matrix representation of the inner products. Let's talk about that. And just to simplify things, let's just focus on the inner product, not the Hermitian one. And then later in the course, we may need to think about what happens if we make the inner product Hermitian. It's not that different. All right. So if I have vector A1, A2, A3, and another vector B1, B2, B3, then the dot product between them is A1 times B1, A2 times B2, and A3 times B3. Oh. And we can rewrite this in the following way. We can take the matrix A1, A2, A3 as a row matrix, and then the matrix B1, B2, B3 as a column matrix. Right? And if you do this multiplication, matrix multiplication, what do you get? You get the exact same thing, the dot product, right? You get A1 times B1 plus A2 times B3 plus B2, A3 times B3. You get a one-by-one matrix where the only value you get is the dot product, right? So you can write it like this, and so if I say the standard unit vectors of R3 is, say, 1, 0, 0, 0, 1, 0, then 0, 0, 1, if it's like that, then we can rewrite it like this. What is this one? This is vector V written under the basis A. That's the symbol that we were using, right? So this one, we were calling it as vector V represented using basis A, right? So we can rewrite what we just had as the following. We have the vector U represented under A, but our matrix coordinate vectors are column vectors, right? Whereas here I need a row vector. What takes a column vector and makes it as a row vector? Remember? Transpose. So we take the transpose, TR, or I think people just use big T. So we take the transpose of this matrix, and then what we do is we're going to stick in an identity matrix, because it doesn't do anything, right? And then multiply V, A, T. Okay? And furthermore, we're going to call this one as the matrix representation of our inner product under A. Okay? So what is that? That's U, A, T, matrix representation of our inner product under A. Actually, this should be A to A, right? Because we have both A and A, but if the domain and the range is the same, we'll just put it as A. And by the way, sorry. If it's a map, then it makes sense to go from one to the other, but inner product is just, it gives you a scalar, and both of these vectors should be under the same base, so you don't need an arrow, it's just a single basis, right? So, okay. So that's what calculates this, right? Okay? So, now let's try to do something else, which is This time, let's say we have another set of bases. Okay. All right. So, yes.
Why do we, if the inner product and the dot product are the same thing, why do we use that notation instead of the dot? If, in terms of like less writing, would it be incorrect?
Oh, okay. So the purpose of what we are doing here is not to make things convenient. My goal is to see what happens to this matrix if you change bases. And ultimately, this is the question. We usually, in the easy linear algebra course, this course is like kind of putting those two together. It's like the exam one was the easy part, right? And then we go to the more abstract, harder parts in exam 2 and afterwards. In the easy linear algebra course, we use matrices as if that's the only kind of vectors that we know, right? But as I have shown in these more abstract settings where you have like a vector space of solutions of differential equations, or vector space of polynomials, stuff like that, vector space of continuous periodic functions. When you have these kind of vector spaces, you really don't have a natural basis. I mean, who are you to say that this is any better than that one if we are working in some strange vector space, right? Yeah. And in those vector spaces, we don't even know how to measure the sizes of vectors. Like, if you have a solution of a differential equation, and we've seen that they form a vector space, but what does it mean for the size of one of the functions that make up the vector space? It's a bit weird, right? But it turns out that those kind of questions do make sense, and that's what allows one to solve PDEs later on. Okay? But in order to be able to do that, you first have to approach the vector space as if you have a vector space and you can come up with some basis on your own, but you don't even know how to measure the size, and you don't even know what to put for the inner product. Okay? And then once you start to define one and another one, one by one, then you look for the properties that you want. Okay? You eventually want to define an inner product as anything that satisfies the three conditions that I said before. What are those? Commutativity, and then linearity in the components, and then positive definite. If those things are satisfied, then you just call that an inner product. And if you have an inner product, then you can always do the things afterwards. Okay? What can you do? Well, we'll talk about it. What this would be. Okay. Which we can spend quite a long time trying to figure out. But then instead of that, let's try to take a shortcut by writing down what we want. Okay. So here's what we know. If I give you any vector u, then you can write down the representation of u under this basis b, right? Take the transpose, right? And then if I give you another vector v and write down the vector coordinate matrix with respect to basis b, and if you do this, what do we want from this? This calculation should be giving us u v, inner product, right? So that should be the same, right? So just as this is true for any vector a, okay? If I replace any basis a, just as this is true for any basis a, if I switch the a with b, this still should be true, right? Okay. But then think about this. If I already have this, I know how to go from VB to VA. Do you remember how to go from VB to VA? How do you get VB from VA? You apply the identity, but the one that changes basis A to basis B, right? This changes things, right? So what we can do is we can take that and then, and then there's another property that I forgot to say about transpose. If you have UB transpose, no, why did I put B here? Sorry. If you have UB transpose, well, this thing itself is still same as I A to B, right? And then U of A, U represented under A. So this takes coordinate matrix under A to a coordinate matrix under B, right? But then when you take the transpose of product of two vectors is same, two matrices is same as transpose of each of them, but you have to swap them. Okay, but that takes a bit of thinking and then doing some examples. So if you do some examples, you'll see that it's indeed true. So you end up with UA transpose times I A to B transpose. Okay? So we get that. And now we're almost there, because I can now replace VB by this, right? And I can now replace UB by this, right? And then let's stick them in here and see what we get. We get UA, U under A transpose I A to B transpose this mysterious matrix under B times I A to B, and then the A has to equal to this. And now if you compare this thing that I just wrote, this much here, with this much here, what do you see? If you just cover this and cover that much, it's exactly the same thing, right? And since this equation should be true for any vector u and v, and this should be true for any vector u and v, these two should be equal to each other. Is that okay? All right. So here's the conclusion I'm trying to draw. Conclusion that I'm trying to draw is that this should be same as this, which was the identity, right? It's this thing. Okay? And now all you have to do is take the inverse of these to the other side so that this thing is equal to inverse of B to A transpose times the identity matrix, I'll just put I, times identity B to A inverse. Okay, but I also know what this inverse is. What's the inverse of I A to B? I B to A, right? So this is going to be, and multiplication by an identity matrix doesn't do anything. So what it does is you end up with identity, so the transition matrix from basis B to A transpose times itself is what you get for this new basis representation. Okay? So now let's actually do it. Because in the last class I wrote this down. Can you tell me what I of B to A is? Exactly this, those three vectors, 1, 4, 1, 1, 2, 0, then 2, 1, negative 2. Okay. Since this is what we have, here's what we get about the inner product with respect to this basis B. Inner product matrix with respect to this basis B. It's 1, 4, 1, 1, 2, 0, 2, 1, negative 2 times its transpose. So it's 1, 4, 1, 1, 2, 0, and then 2, 1, negative 2. Is that right? These switched, these switched, these switched. Okay, good. Yeah. So that's what you get. And if you do this, 1, 4, 1 times 1, 4, 1 is 18. 1, 4, 1 times 1, 2, 0 would be 1 plus 8, that's 9. 1, 4, 1 times. Okay? So that's what you get. But I believe what I just showed you is not in any textbook. I just made it up. Okay? If I were to make a linear algebra textbook, I would do this. Okay? But I don't think I've seen this in any textbook. But there's a lesson to be learned here. The reason I'm doing this is to show you that if you jump into any new world of vector space, so one day you wake up, the world is a vector space. Okay? The world that you live in is a vector space. Okay? And then you're presented with some basis vector. Okay? And then they also say, here's an inner product. But that inner product may not look like this. This represents the standard one, right? A1 times B1 times C1, right? Rather, that inner product might look like this. Okay. Now, what does this mean as an inner product? I guess that's the thing that you should also know. What do I mean when the inner product is like that? Well, it means that, say, if I have one vector, u as A1 times 1, 4, 1, plus B1 times, no, that shouldn't be it. Let's just say that u is a vector where if you write this as A1, A2, under B you get A1, A2, A3. And V under B, let's say this is like B1, B2, B3. Okay. Then the inner product between U and V can be calculated by doing A1, A2, A3 times that vector 18, 9, 4, 9, 5, 4, 4, 4, 1 times B1, B2, B3, which gives you something really crazy because look, what do you get if you do this times this and then multiply this? You get 18 times A1, B1. Instead of A1, B1, you get this. But not only that, you're going to get, I think, let's see, this times this will give you 9B2. 9B2 will also be, now that will be the first one. Yeah. 9B2 will also be multiplied to A1, so that you're going to get 9A1B2. And then you're also going to get 4A1B3. So these terms didn't happen in the regular dot product, right? But these terms suddenly happen. And all of these numbers will give you 6 more terms. Okay? So the inner product that you'll be presented with in some strange vector space would look very different. Okay? But then, what if somebody presents you to the inner product and you can't trust it? Okay. What makes something? Can you write any matrix and it will always be an inner product? It seems like not every matrix, 3 by 3 matrix that you write is going to become an inner product, right? When would it be an inner product? What do you think?
The determinant is not equal to 0.
That's definitely one thing, because if the determinant is equal to 0, this time some vector will give you 0, which will destroy the positive definiteness. Okay, so the determinant has to be actually positive, but it has several properties. So we can only know if a given matrix can be an inner product with respect to some basis if the following is true. If your inner product is represented by some matrix, you can still calculate with it because you can do this, right? So if you make these calculations, you have to just check the 3 things. Is it symmetric, right? Is it linear? Well, linearity will always be true, so because if you write it like that, then it should always be true. So you'll need this to be symmetric. And another thing is that UU should be non-negative. Okay? If these 2 things are guaranteed, then it will be a inner product under some basis. That's the point. Okay? And then this, if you think about what this means, it means that the matrix under this basis, this matrix that we were talking about, this is actually symmetric. And what does symmetric mean? Its transpose is same as itself. Okay? In other words, i.e., if you take the transpose of the matrix, it will be same thing as itself. Okay? So that's one thing. And the second thing about this positive definiteness, it has many different requirements, but the simplest one you can know for sure is that the determinant of all the minors are positive. Okay, so not just the minors, but the determinant from here and then here and then here. Okay, so you build a 1 by 1, 2 by 2, 3 by 3, and if all these matrices determinants are all positive, then there's a mathematical theorem that shows that in that case it will always be positive definite. The only time this will be 0 is when you have the 0 vector. Okay? So that's the next property. Okay? So any kind of symmetric matrix that satisfies the determinant of the submatrix being positive can be an inner product under some basis. Okay. Next time, what we're going to do is we're going to start with some given inner product obtained by some weird inner product rules. Okay. And from that, our concern is, can we find another basis that makes the inner product look nice? And nice meaning it looks like the diagonal 1, 1, 1, the identity matrix. Okay? Then what that enables us to do is, if that's true, then first it makes the inner product calculation a lot easier, but also it allows you to easily represent one vector by another. This inner product makes all kinds of calculations a lot more simpler, but it wouldn't be so simple if your inner product matrix is like this. Okay? So that was the point of today's lecture. Okay?